Hello everyone, welcome to Keep Learning at the Rate Be Creative. In this video, we are going to discuss a very interesting geometry problem from IOQM exam. In an equilateral triangle of side length 6, pegs are placed at the vertices and also evenly along each side at a distance of 1 from each other. 4 distinct pegs are chosen from the 15 interior pegs on the side. That is, the chosen one are not the vertices of the triangle, and each peg is joined to the respective opposite vertex by a line segment. If n denotes the number of ways we can choose the pegs such that the drawn line segment divide the interior of the triangle into exactly 9 regions, we need to find the sum of the square of the digits of n. So let's see how are we going to solve this problem. So we have to consider an equilateral triangle and pegs are placed at the vertex and also evenly along each side at a distance of 1 from each other. So let us consider an equilateral triangle. Here we are going to place the pegs at the vertices A, B and C, and there are 15 pegs in the interior of the side which are evenly placed. So here you can see that we have placed the pegs, and let us number them from 1 to 15. Now, according to the question, 4 distinct pegs are chosen from the 15 interior pegs on the side and not from the vertex. That is what we have to remember. And each peg is joined to the respective opposite vertex by the line segment. So in this case, we are going to get 4 Cevians. Now, these Cevians should divide the interior of the triangle into exactly 9 regions as shown here. Here you can see we have chosen peg 3, peg 9, peg 12 and peg 14, and when we have connected them with the opposite vertex, here you can see that the triangle is being divided into total 9 regions. This is 1, 2, 3, 4, 5, 6, 7, 8 and 9. Now we have to find out in how many ways we can do this. For this following cases, we will be considering. First case will be, we will be choosing 2 pegs on first side and 2 pegs on third or the second side. And will be choosing in such a way that no 3 Cevians are congruent. So here we have the triangle ABC. So here we have chosen these 2 pegs on the side BC and the other 2 peg on side AC. So here you can see that the number of region in which this triangle is being divided, that is 1, 2, 3, 4, 5, 6, 7, 8 and 9. So yes, we can consider this case. Let us see another way in which we can choose the pegs. Here you can see that we have chosen 2 pegs on the side BC and the 2 pegs on the side AB. So here again we can see that the number of region in which the triangle is being divided is again 9. So we can consider this case. Now we need to know that in this particular case, how many ways we can consider. Now the number of ways in which this can be done, that is selecting any 2 points on any 2 sides, that is number of ways will be 3 times of 5C2 into 5C2. 5C2 represents selecting 2 points out of these 1, 2, 3, 4, 5 points from one side, and the second one represents second 5C2 represents selecting 2 points from these 1, 2, 3, 4, 5 points. Now we are multiplying by 3 because selecting 2 sides can be done in 3 ways, that is selecting AB and AC, or selecting AC with that BC, or selecting BC and AB. So here the total number of ways comes out to be 300. Second case could be selecting 2 pegs from first side, 1 peg from second side and 1 peg from third side, and no 3 Cevian are concurrent. So here you can see that this is the triangle, 15 pegs, selecting 2 pegs on one side, 1 peg on the other side, and on the third side again we are selecting 1 peg. Now let us see in how many regions this triangle is being divided. So here you can see 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So this triangle is being divided into 10 regions. So we don't have to consider this case because we need exactly 9 regions. Let us take another way. So if we select 2 points in this side BC, one on AB and one on AC. In this case, again we are going to get the 10 division. Here you can see 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So we are not going to consider this case. So let's see the next case which can be formed. Again here we are taking the same type of case, but here the condition has changed. That is 2 pegs on first side, 1 peg on second side, 1 peg on third side. But here we will be taking 3 CV out of 4 concurrent. So here you can see this 2 CVNs we have selected and 1 CVN again we have selected, and this next CVN which we have selected, and these 3 CVNs are concurrent. Now here you can see that the triangle is being divided into 9 region, which is the requirement. Let us see one more figure. If we select 2 pegs on this BC, 1 peg on AC and 1 peg on AB, keeping in mind that 3 CVNs are concurrent. So in this case again we are going to get the 9 divisions. Now for concurrence of the CVN in a triangle we need to use Ceva's theorem, because here you can see the region is being divided into 9 parts only when the 3 CVNs are concurrent. So for concurrency we will be using Ceva's theorem, condition of Ceva's theorem. So here according to Ceva's theorem we know that A upon B into C upon D into E upon F should be equals to 1. What do we mean by A, B and C, D and E, F? Here let's see. So if it is a triangle and these CVNs are drawn which are dividing the respective side in the ratio A is to B, C is to D and E is to F, then the product of these ratios come out to be 1. Now for the product to be 1 we can consider 2 types of cases. Here the ratios, the 3 ratios can be A upon B, second ratio should be B upon A and the third ratio should be 1 upon 1. In this case you are going to get the product 1, or you can select all the 3 ratios at 1:1, 1:1 and 1:1. Again the product comes out to be 1. So this is the condition for the concurrency of the 3 CVN in a triangle, which is Ceva's theorem. So let us see in how many ways we can do this for the given triangle. Let us first understand with an example that what do we mean by the ratio and the product comes out to be 1. For example, here we have this triangle. Here you can see these are 4 parts and these are 2 parts. So BC is being divided in the ratio 4:2. Again here you can see that AC, here we have 2 parts, here we have 4 parts. So it is divided into 2:4 ratio. And similarly for the side BC, it is divided into 1:1 ratio. Here you can see if we take out the product of these ratios, that comes out to be 1. So now we can choose the ratio 1:1. So we have to choose one ratio as 1:1. Here you can see. So there can be 3 ways. We select the midpoint of each side. That way we can do. So there could be 3 ways. So selection of 1:1 ratio, and there can be 4 ways to select the ratio A is to B or B is to A. That could be 1:5, 2:4, 4:2 or 5:1. Here we have taken the ratio 4:2 as an example. Now number of ways in which this can be done will be 3 into 4. 3 ways of choosing 1:1 and 4 ways of choosing A is to B ratio, and that B is upon A ratio will depend on A upon B ratio only. So therefore total number of ways here will be 12. One more case which we have discussed, that is if all the 3 ratios become 1:1. So there can be only one way when all the 3 midpoints are being connected to the opposite vertex. So total number of ways in which the 3 CVNs can be concurrent will be 13 ways. Now we have one more CVN left, that is the 4th peg which we are going to connect to the opposite side. And let's see how many pegs are now remaining. So here you can see if we connect this 4th one, we can take either 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So we have 12 options for the 4th CVN. So here you can see for the 4th CVN we will have 12 C1 ways, which comes out to be 12 only. So total possibilities will be 12 into 13, that is 13 is the number of ways for the concurrency of the 3 CVN and 12 is the number of ways of selecting the 4th CVN. So that's why total number of cases comes out to be 156. So total cases possible will comes out to be 300 plus 156, that is 456. So the sum of the square of the digits of 456 will be 4 square plus 5 square plus 6 square. That comes out to be 77, which is the final answer for this question. Now this is a question from IOQM where the 2-digit integer answers come. So here the final answer comes out to be 77. So it's a very interesting problem based on geometry as well as combinatorics. Thanks for watching the video. If you like the video, please subscribe the channel for more videos. Thank you.